So I thought my my video of yesterday would be my last one, but I got a few remarks and I want to make a very short one to respond to them. One of them is that I try to cover too many topics probably in my videos, and the other one is a little bit on this proton yarn ball puzzle, as I call it. So we have I think that's a major feat. The proton radius got experimentally measured in various ways, and we have a finite measure for it from experiment. That measure corresponds to what I write here, a theoretical radius that I derived directly from Einstein's mass-energy equivalence relationship, and then a rather special but not so special Planck-Einstein relation, where instead of the energy being equal to h bar times a frequency, is 4 times h bar frequency. So you might say we get a lot more energy if you write it in the other way. E divided by the frequency, we get 4 times Planck's unit of action. And but the idea is the same, that a proton would be like a ring current, except that it would be a ring current in 3 dimensions, and in 3 dimensions, not just because the ring current is sort of drifting around its own axis, but because it's an oscillation in 3 dimensions, and that's easily said. But there's no easy formula when you try to, develop the equations of motion for the point-like charge inside that ring current. That's very easy to do for an electron, for a ring current. Any textbook will give you, the easy equations for that to calculate the magnetic moment, because a ring current is indeed like a tiny little magnet with a north and a south pole orientation. So a little dipole. For the proton model, we do get, I said, that radius, 4 times h bar divided by mc, or if you want to write in energy, 4 times h times the energy of the proton divided, h times c divided by the energy of the proton. You can't see it. Let me try again. So that's easily said and done. And then in this paper, the proton yarn puzzle, I do try to find sort of a trajectory. I said, okay, this charge must be zooming around on a spherical surface, and that sort of vaguely I explained also. So this 4 factor would be indeed just the factor that you have for the area of a surface, which is 4 times pi r squared, the radius of the versus a circle, which is just pi r squared. So the ratio of that is 4, and that sort of geometrically makes sense. But the you want to develop those equations. And that's a problem I wanna leave with you, that people saying like, look, that should be quite easy. Huh? There's lots of very good. This is from MIT OpenCourseWare, where they give you acceleration vectors, velocity vectors, and whatnot, based on a spherical coordinate system, where you express the position of a point in terms of a distance from the center, the origin, and the 2 azimuthal and polar angles. Or from Libre texts, you have that. Now the thing is, I really try to do that in that paper, and the thing is, analytically, it's not so easy, and I will explain in a moment. I will show you sort of what I do to sort of make sense of these things. I do play with the 3D graphing tools. This is a very nice one, Desmos. It's free. I warmly recommend it. And so here's what I show, is that indeed, if you model a point like a charge in this point, and you use these spherical coordinates, here we normalize the distance at 1 from the origin. A sine times a polar angle times the cosine of an azimuthal angle, the other way around, and then the sine times the sine, and then the cosine of your first angle. You do get yeah, something that you know, goes around or seems to go that goes on the surface area of a sphere with radius 1. But the relationship that you have here is where that angle must be a function of time as the charge moves around. And then, you know, an easy frequency formula where you say like the angle changes at, you know, a certain frequency A times the time, and the other angle changes at, you know, a certain frequency B times the time plus, you know, you can add a phase difference of, let me do that here, yeah. A delta, which is equal to pi over 2 or something, some other angle in between. So you do get a spherical trajectory, but as you can see, the velocity of this point-like charge, what I think of, is not constant. And that's, of course, what we want to have in our model. Let me show that. I'll come back to a few notes later. This is sort of the situation which you wanna model, really. Yeah? So we have a distance a, the proton radius equal to 4 times h times c divided by the proton energy, and then we have this frequency given by our special Planck-Einstein relationship, which is not so special. Planck-Einstein's relationship for discrete energy states is n time. The reduced Planck unit times the frequency. So in this time n is 1, and that's where I say, well, you go from 1 to 4 when you go from an electron to a proton. So the challenge is that, or the constraints in my theoretical model is that indeed the tangential velocity of that charge is you know, the speed of light. And the direction of the tangential velocity, you know, changes. And we must write it as a vector product then of this radius vector times, and this is an pseudo vector, the frequency vector, and we know that this will be orthogonal to the radius vector, orthogonal to the velocity vector, and so we have a vector product where there's no sign of cosine. We can just, the magnitude of our velocity vector will of course be equal to c, speed of light, times yeah, the radius distance times the absolute value of our frequency vector. So that's all nice, but it means that you know, what we want to do is you know, find a trajectory in terms of let me go. So I copied from that MIT open course where the main formulas for well, the distance is fixed, the velocity is fixed, the radius is fixed. What is that? No, that's an acceleration vector here in this case. So sorry for the symbols. That's another thing, you know, spherical coordinates. Sometimes you will see the azimuthal angle measured from the XY plane, and sometimes you will see it measured from the YZ plane. But these are the formulas that I use in my Desmos animation. And I said what you find out is that you know, you want to write the two angles in terms of a function of time, and you cannot do what you would do with a linear oscillator or you know, a ring current, and that is just to write this angle as you know, some frequency times the time. The frequency is the frequency, its direction changes, and so you cannot directly you know, relate the frequency vector that I have in my proton model to you know, these two angles, the azimuthal and the polar angle. You cannot write sort of simply that you know, delta is equal to some kind of omega delta projection or whatever times t. No, it's a much more complicated function. And then the other problem is, when you want to develop a model like that, is that you know, I said the idea behind the electron model is that, and that can be easily shown, is that the electromagnetic field that is the ring current creates is at the same time also the electromagnetic field, or the magnetic field, I would say, that keeps the current, the charge, going around and around. Now, the electromagnetic field that is generated by a current in 3 dimensions, with all the forces that act on it, you know, there's no easy formula for that. There, you need to go to the general solutions to Maxwell's equations. Maybe there is a solution for it. I hope to find it, but these Leonhard Wichet, is a German-French tandem of scientists who develop general solutions to Maxwell's equations. And yeah, these are difficult integrals, and you need to apply them to this simple but at the same time very complicated geometrical situation. So that's all I'm gonna say about it. To the people who say like, "Wow, it should be very easy," huh? Well, no, and this is what I explore in this paper that gets very few reads, and I must admit I probably wrote it with a beer too much. But yeah, I explore sort of models that are around. I said there is a toroidal model rather than a spherical model of the proton, and that's sort of that's Andras Kovacs and Giorgio Fasallo, someone whom I admire very much, an Italian quantum physicist. So their model works. It's a helical solenoid model. I just don't like it, I said, because you have 2 frequencies in such model. It doesn't give you you know, something that is consistent with the packing models inside of nuclei. Based on experiment, at least that's what I gather. Protons, neutrons, nucleons, and nuclei itself, composed of various nucleons, seem to be spherical, and that's where I like my simple model, which I put here again, 0.841 femtometer. Yeah, it should be a spherical model, but yeah, not so easy to derive. So I'm gonna leave it at that, and just explain sort of this is the geometry of the problem, and I have not succeeded in doing what I did for the electron model, and is to find very simple equations of motion for that point-like charge, and show that the motion of that point-like charge on that in that spherical model generates the electromagnetic field that would keep that charge going the way it goes. And so that's an interesting problem. I'm frankly the first to admit that I'm not so good at that math, but this is sort of a project I want to postpone. I think about it, but it's clear the math you will need will be pretty advanced. I want to finish this video so with a few points that I didn't touch upon yesterday. I talked about you know, matter antimatter annihilation, and I said like you know, this theory, the Dirac process, where an electron and a positron annihilate each other and generate 2 gamma rays. I don't like that, and I suspect that the 2 gamma rays may carry the charge, that charge actually doesn't get destroyed. And I said that's maybe where you know, this theoretical W plus minus bosons aren't real bosons, or they aren't really photon-like. But I want to show again of Giorgio Vassallo again, who shows actually, you know, when you have an electron model, a Zitterbewegung model, and then you inject, you're going to accelerate it through electromagnetic fields, and there's going to be a lateral component to the velocity, the tangential velocity, then you know it's going to become indeed, you know, more spiral-like, but the radius has to decrease because yeah, the speed of light is the speed of light, and as the tangential velocity gets this lateral component, then the radius of our electron must become smaller. So it becomes smaller and smaller and smaller, and at very, very, very high speeds actually. And I think this explains relativistic length contraction, perhaps in a physical way, because of course we can imagine that the polarization of the electron would be something different, but you know, then we get a more complicated structure, but still something with a radius that becomes smaller and smaller. So if you go to V over C ratios that go very near the speed of light, and we know we need enormous energies to do that, and as a result also the mass, the relativistic mass of our electron will increase. So our electron does become photon-like, and the radius increases, but of course this is not a photon. It's photon-like in the sense that it travels at very nearly the speed of light, but it's also very massive. So I was thinking that you know, matter-antimatter annihilation, I look forward to experiments, might be explained by the, you know, two outgoing gamma rays that you get. Maybe these W plus minus bosons, and these bosons might combine speed very close to light, and then indeed a tiny little charge which seems to have a very, very, very small dimension in the limit. It's Lorentz or Thomson radius on the classical electron radius, so very, 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 very small and tiny. And so in experiments it might appear to be a very massive photon, but it would carry charge. I have no evidence for that. I said I touched on many things in my writings, and I readily admit that I don't always have the time to you know, double check what I think. So I'm gonna clean up my sheet and leave it at that. So it's a very short lecture. I hope it makes up for what people say. Don't make your videos too long. Focus on a specific topic, and that's it. I just want to have maybe one loose end. In this model, there was a remark also made. It sort of, he says, it's kind of funny. If you have you know, an oscillator model like that, usually the energy in an oscillator is gonna be proportional to the square of the amplitude times the square of the frequency times a proportionality factor that, you know, in a classical spring problem is going to be 1 over 2 times the mass. I argue that in my electron model, the mass is the effective mass of the electron, which is the mass of the electron divided by 2, whereas the rest of the energy in the electromagnetic field that keeps that charge spinning. So we have kinetic and potential energy in this two-dimensional oscillator. But the thing is, you know, your Compton radius formula says that your radius is inversely proportional to the energy. Well, here you would say like energy proportional to the square. So how does that work out? It works out very easily, because we have indeed a frequency factor that sort of makes up for it. We have the Planck-Einstein relationship, and then indeed sort of that E is mc square if we replace it by our tangential velocity formula, a times omega squared. When you work it all out, you see indeed that you know, these two combined do give you a Compton radius, which makes the difference between an electron and a proton. It's much more massive, because the energy, the mass of a proton is much more massive, and it has a much smaller radius. The thing is also, you know, when you look at a photon wavelength, the photon wavelength is also going to be inversely proportional to its energy. We know that photons, very high energy photons, have very short wavelengths. So high energy, short wavelength. So the formula is consistent, although intuitively, you know, it may not have come across your mind. You think like, well, okay, high energy, higher, big amplitude, but bigger things, more energy. Yes, but it does not apply to the world of elementary particles. So these are the two things I wanted to add to yesterday's video, and I'm going on the bike now, and I wish you a very nice day.